Now that we know about the sine and cosine of all sorts of different angles, we're going to now graph them to take a look at what they look like. So by the end of this lesson, you should be able to graph sine and cosine functions. So just the basic function without transformations. Determine the period, amplitude, max, min, domain, range, and zeros of the sine and cosine function. Understand the similarities between the sine and cosine function, and predict the amplitude and period of a sinusoidal function given its equation. So that would be with some transformations. Let's start off by graphing the sine function. So to graph any function that we don't know what it looks like, all we have to do is plug in random values for x into the function and see what pops out for y. So the easiest angles to do that with are the angles that we know the exact value of sine and cos, which are going to be the angles in our special triangle that we have depicted on our unit circle. So take out your unit circle. I've added one here just so that we can see it visually. So let's take a look at the sine value of, let's go up by 30. So let's take a look at 0, 30, 60, 90, 120, 150, etc. And we'll go all the way to 360. So we can remember that on the unit circle, our y value is going to be the value of sine for that angle. So that means that the sine of 0 degrees is going to be 0. So let's add that into our chart. The sine of 30 degrees, that's just going to be a half. The sine of 60 degrees is going to be root 3 over 2. And the sine of 90 degrees is going to be 1. So go ahead and complete the first row of this chart on your own. So now that you've got your chart complete, it's hard to graph the point 60 and root 3 over 2. So let's change all of these exact values to approximate decimal values. So maybe we'll take 2 decimal places if we need to. So for example, 0, we know the exact value, that is 0. We know 1/2, that's equivalent to the decimal 0.5. And if we divide root 3 and over 2, we're going to get 0.87. So let's continue that for the rest of these values. So now that we have all the decimal values, we're ready to graph. So taking a look at x, we're just going to graph one complete cycle. So we're just going to graph the sine values from 0 to 360. So we just need to go up to 360 on the x-axis. So why don't we go up by 15 degrees? So every 2 squares we're going to make worth 30 degrees. So let's add in our scale here. So we've got 30 degrees, then skip 2 squares and 60 degrees, and continue. Now that we have the x-axis plotted, let's label that. This is going to be theta, and theta is going to be measured in degrees. So now taking a look at the y-axis. So what is the maximum value that y can take on? So let's take a look at our decimal values. The highest value of y is going to be 1, and the smallest value of y is going to be -1. On top of that, we've got to plot this tiny little number 0.87. So why don't we go up by 0.2s? So we'll have our first square is worth 0.2, our second square is 0.4, and etc. So once we've done our scale, don't forget to label it. So this is going to be sine of our angle theta. Now we're ready to graph. So we're going to take our points from here. So our first point is going to be our x value is 0 and our y value is 0. So we're going to do a big dot at 0, 0. And our next point is going to be 30 degrees and 0.5. So our next dot is going to be somewhere around here. Then we have 60 and 0.87. So approximately right in the middle there. So continue like this until you've plotted all of the coordinates. So once you're done, you should have the dots align in this symmetrical curve that we can connect with this curved line like that. And this is what the sine curve would look like. So we know that if we go around the unit circle again, so past 360, if we were to add another 30, for example, and another 30, etc., all of these values would just repeat as we go around the circle again. So what this is going to be a periodic function that's going to continue to repeat and repeat and repeat. So moving forward, we're going to have to be able to graph this very quickly because we're going to apply transformations to it on top of that, we're going to use this graph to model real life situations. So we have to be able to graph this fairly quickly. So to do that, the easiest points to remember and to graph are the x-intercepts. So we have an x-intercept at 0, we've got an x-intercept at 180, we've got an x-intercept at 360, and the maximum and the minimum values. So this is a symmetrical function, which means that our maximum is going to be perfectly in the middle of our two zeros, as well as our minimum value of -1 is going to be exactly in the middle of our two zeros on the right. So if we can remember these 5 important points, we've got our 0, our maximum, our next 0, minimum, and our final 0, then we'll be able to graph this sine function fairly quickly. So now let's take a look at some of the properties of the graph of sine x now that we do have the graph in front of us. So first let's start off with the maximum minimum values. So our maximum value of sine is 1 and our minimum is -1. So our max is 1 and our minimum of -1 is -1. The max occurs when our x value is equal to 90 degrees. So this max happens when our x is equal to 90, and the function reaches minimum value when its x is equal to 270 degrees. Next, for domain and range. So we've only graphed one cycle of the sine function. So we've only graphed till 360, but we know that this can go on and on and on and on as long as we continue increasing our angle. And even in the negative direction. So if we go clockwise around the unit circle, then our angles are going to be negative. And -30 and -60, -90, they all have values too. So this is going to continue on in the negative x's as well, which means that the domain of sine x is that x is an element of R. Theta, or x, can take on any value. So we've added in our domain, which is x an element of R. Now let's take a look at our range. So we can see that the maximum value of our y is 1 and our minimum value is going to be -1. Since this is periodic, that means the y values are going to continue to repeat, which means it's going to continue to bounce in between 1 and -1. So our max is 1, our minimum is -1, and we know that we can write that as a as a range as y is an element of R such that -1 is less than or equal to y is less than or equal to 1, which means y can take on only values between -1 and 1, and it can be equal to -1 and 1. Taking a look at x and y intercepts, we can see that we have x-intercepts of 0, 180, and 360. So those are the ones we have listed here. However, that's only if we have one cycle graph. If we have multiple cycles graphed, then we're going to have x-intercepts at any multiple of 180, which means if we keep on adding 180, so to 360, if we add 180 to 360, we get 540. We're going to see x-intercepts. In terms of our y-intercept, there's only going to be one. It's only going to cross this x-axis one time at 0. So because we know that our graph is periodic, because the y values are going to repeat, we know then it's going to have a period, an amplitude, and an equation of the axis of symmetry. So we remember that a period is just the length of one cycle. So one cycle of our sine curve takes up 360 degrees. In terms of our amplitude, we know that the amplitude is the distance from the maximum to the middle of the graph and the minimum value to the middle of the graph. To calculate that, let's first come up with our equation of our axis of symmetry. So we know that's going to be the line that's going to cut this graph exactly in half in terms of the y values. So visually we see that it's the x-axis that's going to cut this graph exactly in half. Mathematically, we can calculate it by subtracting the maximum, adding the maximum and minimum and dividing by 2. So 1 plus -1 is going to be 0, divided by 2 is going to be 0. So our equation of our axis of symmetry is just going to be y is equal to 0. Therefore, our amplitude is just the distance from the maximum to the x-axis, or the line y equals 0, which is going to be a distance of 1. And it should be the same distance from the minimum to that axis, which is also 1. So therefore, it has an amplitude of 1. So now that we have the sine graph or the sine function graphed, let's graph the cos function. So we're going to do it in the same way. Let's start off with our unit circle. Remember, in our unit circle, all of our x values are going to represent cos. So let's plot the same values of x. So let's go by 30. So we've got 0 degrees, 30 degrees, 60 degrees, 90 degrees, because we know the exact value of cos for all of those. And let's start filling in our chart. So we know, for example, that the cos of 0 is going to be 1, because we see it right here. And the cos of 30 is going to be root 3 over 2. So now continue filling out this chart on your own and then check back in to make sure you've got the right solutions. Now that we have the exact values for cos for all of those different x values, now let's approximate their decimal values like we did before. So we know that the decimal value of 1 is 1, and we know that the decimal value of root 3 over 2 is 0.87. So let's continue this chart so that we can graph it. So now that we've got all the decimal values, we're ready to start plotting. So taking a look at our x values, again, those are just our angles. So we might as well go up with the same scale that we went with when we were graphing sine. So let's go up by 15 degrees on our x-axis, and taking a look at our y-axis, again, our maximum value is 1 and our minimum value is -1, and we have to graph those annoying 0.87s. So why don't we again go up by 0.2. So go ahead and draw on your scale and then come back to the video. Now that we've got our scale, we're ready to plot. So here's going to be our first point. In our x-axis, we're going to have 0, and our y-coordinate, we're going to have 1. So our first point, cos, is now going to start up at 1 instead of 0, like it did for sine. So our next point is going to be 30 and 0.87. So 30 and 0.87 approximately would be there. Then we have 60 and 0.5, and 90 and 0. So let's continue graphing this. So once we've got that graphed, we have a new curve. It's shaped almost like a bowl. But notice that it's the same values of y as what we graphed for sine. The patterns were 1, 0.87, 0.5, 0, and then the negative versions, which means that these have the exact same shape. Cos and sine are the exact same shaped curve. It's just that sine begins at the point 0, 0. So the sine curve starts actually right here and continues to go up and down. So if we were to continue this cos curve, maybe if we have multiple cycles, so one cycle, another cycle here, sine starts right here. It comes up, it comes down, and comes back again. Cos just starts at the maximum value at 1 and dips down and comes back to 1. But the y values are exactly the same, which means the cos curve is just the sine curve shifted to the right 270 degrees, because here's sine right here. So now that we've got the cos curve graphed, let's compare its properties to the properties of sine. So fill in these properties on your own and then come back to the video to check your answers. So starting with the maximum and minimum, cos and sine have the same maximum value, that's positive 1, and the same minimum value, -1. They just happen in two different places. So for cos, that maximum happens at 0 as well as 360. So let's add 360 here. And the minimum value happens at 180. So the domain of cos and the range of cos are also going to be the same as sine. If we think about it, if we go beyond 360 degrees, so we go around the unit circle one more time, we know that these y values are just going to repeat over and over and over again. So this is a periodic function that's going to continue for all values of positive x. And we know if we go clockwise around the unit circle, we're going to get negative values. And again, these y values are going to repeat, which means that x can take on any real number. So x can take on any real number, and the range, same as sine, it's going to bounce, our y values are going to bounce back and forth between 1 and -1, 1 and -1, which means that y is an element of R such that -1 is less than or equal to y is less than or equal to 1. So to finish off, our x-intercepts are going to happen at 90 and at 270, and our y-intercept is going to be 1. Remember, for sine, our y-intercept was 0. That's what our first point of the sine graph was. Our first point of our cos graph is going to be 0 and 1. So because the y values are going to repeat over and over again, this is going to be a periodic function, which means that it has a period, an amplitude, and an equation of the axis of symmetry. So our period, just like the sine function, is 360 degrees. That's the length of one cycle, and it's going to repeat over and over again. Our amplitude is 1 because our axis of symmetry is also the line y equals 0. Therefore, the distance from that line to the maximum is 1, as well as the distance from the line to the minimum is also 1. So just like for sine, we're going to have to be able to draw cos fairly quickly so that we can apply transformations to it and we can use it to model real world situations. So the most important points to graph are, again, our maximum minimum value. So we have our maximum value at 1 and 1 as well here, and then our minimum at -1, and then again our x-intercepts. We have that happening at 9 and 270. So just like in the sine curve, there will be 5 points that are really important for us to remember and in order to graph the cosine function fairly quickly. So now that we know how to graph the sine and cosine function, let's start with a few very simple transformations. So we see these letters A and K that we should recognize. A, we know, represents our vertical stretch or compression of our graph, and K is going to represent a horizontal stretch or compression. In a sinusoidal function, A and K have other meanings as well. So we know that A is a vertical stretch or compression. It also represents the amplitude of our function. The reason why that works is because our maximum value of a sine function or cos function is 1. And when we multiply that y value by whatever A is, it's going to become whatever the value of A is, because 1 times A is going to be A, which means that the new maximum value without being shifted is going to be A. So that means that A represents our vertical stretch or compression. It also represents our amplitude. When we take a look at K, we know that K is either going to horizontally stretch or compress our graph, which means that all our x values are going to be divided by K. So we know that our period represents the length of one cycle, so the length of the x values of one cycle. So if all of our x values are going to be divided by k, that means our period is going to be divided by k as well. And because sine and cos both share the same period of 360 degrees, if we have a k value, then we can find our new period by just dividing our original period by k. Because remember, that k value is going to divide all of our x values. So in summary, A and K have the exact same meaning in sine and cos functions as they did in all the other functions that we've learned about. However, they have an additional meaning that we can use to graph sine and cos functions. A, we also know is going to equal our amplitude, and K is going to help us to determine our period. So let's use this newfound understanding in this newly transformed graph of sine. So we have an A value of 2 and a K value of 9. So that A value of 2 means that this is going to have a vertical stretch by a factor of 2. And this K value of 9 means we have a horizontal compression by a factor of 1 over 9. So all of our x values are going to be divided by 9. So if our A value is 2, we know that's a vertical stretch, but that also means that this is our amplitude. Because A is equal to 2, this implies that our amplitude is also equal to 2. And if our K value is 9, we know that this is going to result in a horizontal compression. What that means is our period is going to go from 360 to 360 divided by 9, which is 40 degrees. So now this cycle is going to be squished into 40 degrees rather than stretch out over 360. So now, what if we're given the amplitude and period? Can we come up with an equation for a cosine function? So this specifies to use cosine, so that's what we're going to use. So we know that whatever our a and k value is, we're going to put it into our cosine function. So we'll look something like this. We'll have a cos of, and then we'll have some sort of k value of x or theta. So if our amplitude is 5, that's what we're given here, that implies that our a value is going to also equal 5. If our period is equal to 240, well, we know that our period originally is 360 degrees, and we're going to divide it by whatever our k value is. So if we know the period is 240, then we just have to solve for k. So we can either cross multiply here, or we can multiply by k on both sides, and we're going to be left with k is equal to 360 and divide that guy by 240, which means that our k value is equal to 1.5. So if we were to put this all together, we have our equation would be y is equal to, our a value is 5, and we know we're using the cos function. We know our k value is 1.5, and then we have our input, which is x.